Yeah, so we're going to talk about how to read domains and ranges from the graph. Okay, so give yourself this coordinate plane here, and give yourself the points from -2 to 6 on the x-axis, and from -2 to 4 on the y-axis. And notice the point 6, 4, this is an open circle over here. I didn't do a very good job of drawing it like that, so here we go, put an open circle right there. So give yourself this coordinate plane, and we're going to try and figure out what the domain is, and what the range is, and how do we read them from a graph.
Is this how we write functions on graphs?
Yeah, exactly. Okay, so for the domain, we're talking about all of the x values, right? And so what we want to do is imagine that you take this graph, okay, and you squish this graph onto the x values, onto the x-axis. If you did that, you can imagine that the entire axis from the points -2 to 6 would be sort of lit up by the graph. You guys agree with that? Can you guys visualize that? Well, that right there represents what your domain is. That's your domain, everything that is lit up, all right? So the way that we write it is like this. There's two ways. We can say our domain is all real numbers x, such that such that -2 is less than or equal to x, which is strictly less than 6. Now, why did I say it was strictly less than 6? Yes, sir. What do you think? Yeah, because there's an open circle at when 6 is, right? So 6 is not necessarily part of the domain in this case. The other way that we could write it is like this. Bracket, -2, 6, with a parenthesis. The bracket is used if the -2 is included in the graph, and the parenthesis is used if the point is not included. So in this case, the 6 is not included, so we would leave it just like that. Now, for range, we would do the exact same thing, except we would squish the graph onto the y-axis. So if I squish the graph onto the y-axis, you can imagine all of these points right here would be lit up on the y-axis. That right there indicates your range. So when we're talking about range, we're talking about y values. So we would say the range is all real numbers y, because we're talking about y values, such that -2 is less than or equal to y, which is less than 4. Now, why did I say it was strictly less than 4? For the same reason we said for the domain for x up there. So, if I was going to write this in the interval notation, it would be -2, 4 parentheses. So this top one, that's called inequality notation because there's an inequality in it. And the second one here, that's called interval notation because there's an interval. So inequality versus interval, and you got to know both of them. You're more likely to see the inequality notation than the interval. Okay, so here's a function I gave you. How do you know this is a function, by the way? What indicates that it's a function? Yeah, it passes the vertical line test, so we're good to go. So we definitely know this is a function. Okay, I would like you to quickly now write down what will be the domain for this function and what will be the range for this function. And I need you to write it in both. Okay, so to check, make sure we have here, we should have all real numbers x such that 1 is less than x less than 8. And those are both not points included on the domain, because if I were, again, to squish these points down, I would have all of the x-axis illuminated right there. That would be my domain. And this point from here all the way squished down to here would be my range from -1 to 4. We do not include the 4 in the range, and we do not include the 8 in the domain. So the other way we could write this would be -1 with a bracket, comma. All right, when we're talking about the zeros of a function, what we're doing is we're asking ourselves this question. We're saying, what value of x will make f of x equal to 0? That's the question that we're trying to answer when we say the zeros of a function. The zeros of a function are also the same thing as the x-intercepts, which I'll show you on the graph. So, as an example for us to work with here, so part A, if we said we have this function, this quadratic function, it's equal to 3x squared minus x minus 10. And we want to know what the zeros are of this function. Well, what we're asking, we're saying, well, what values of x that if we plugged in, we would get 0 out of our function. So how do we do that? Well, we set 0 equal to our actual function itself. And in this case, we have a quadratic. So I know I'm going to have to factor this quadratic. So we have to go reach back into our files here. Remember, how do you factor a quadratic? Anybody think they could do it right now? Factor in that? What would it be?
3x.
3x, very good. And an x? Yep.
And then 5.
Probably a 5 and a 2, right? Okay, then what? How do the signs go? Yes. Plus 5 and a negative 2. All right. How do we check this to make sure that this is correct? We go 3x times x. How much is that? 3x squared. Good. What's 3x times a negative 2? Negative 6x, right? What's a 5 times x? Plus a 5x, and then finally, what's 5 times negative 2? Does that add to a negative 1x? Yep, sure does. So we did it right. So I can erase all this stuff. Good, we did it right. Good. Now I can continue ahead and try and solve this. I can say, all right, what values of x is going to give me 0? Well, in this case, either 3x plus 5 is going to be 0 because I'm using the 0 product property, or x minus 2 is going to be 0. So I can quickly solve and get negative 5 halves and 2. So therefore, what we're saying here, yes, sir? No, 5 thirds, thanks. So what we're saying is that f of negative 5 thirds will give us a 0, and f of 2 will give us a 0. So that means that if I were to plug a 2 in for x and x, I would get 0 out. And likewise, if I were to plug a negative 5 thirds in for x and x, I would also get a 0 out. So let's examine this, what this looks like on the graph, and I already have it set up right, there it is right there. Check it out. See this one? 3x squared minus x minus 10. So I'll go ahead and copy this and bring it over to our notes. And there it is right there. So check this out. Do you realize that the negative 5 thirds, there's negative 5 thirds right there? Do you guys see that? And then the 2, there's the 2. So those are also the x-intercepts of the graph, and 0. Okay, so to get back on track here, what did you guys come up with for f of x equals the square root of 10 minus x squared? What are the zeros here? Okay, so how do you do it? What do you do first? Anybody?
I just plugged it in a graph.
0 equals the square root of 10 minus x squared. Then what am I going to do? Yeah, we're going to square both sides. So that means that 0 is now equal to 10 minus x squared. Then what do I want to do? Okay, so x squared has to be 10. Then what do I have to do? Take the square root. So that means that x has to be plus or minus the square root of 10, right? That's an x. Plus or minus the square root of 10. So I have 2 zeros. So that means that f of negative square root of 10 will give me a 0, and f of the positive square root of 10 will also give me 0. So when we graph this in our calculators, and please take your calculators out right now, we'll do it right now together. So that's not the one I want. Sorry, I want the other one. There it is. Okay, so come here. Oh no, how do I grab you? I can't grab you. Oh. I can't grab you. Boom. Okay.
I didn't have to put the right bracket.
Yeah, sometimes you have to do that. So, there we go. So we're getting this sort of like umbrella shape thing, right? And if we actually examine this a little bit closer, for the square root of 10, like this one here, the square root of 10 is about 3.162. And this graph, if you zoom in a little bit, look where is this going to hit? About 3. There you go, right? So if we go down, now this graph, if I keep zooming in, where's that little line? See where it's aiming? 3.162. It's just like, because it goes vertical, it starts to not draw a line there. So the square root of 10 is about 3.162. All right, we're doing pretty good. So the zeros are plus or minus the square root of 10. So what do you guys feel about that? Pretty good? You guys got that? You guys feeling good? Hello? Yeah? Okay, so I have this function. There are 3 parts to this function. There's an increasing part, there's a decreasing part, and there's a constant part. Now, how do we read graphs? We read them from left to right. So we read graphs from the left to the right. So if that's the case, then this one over here, this part, would that be my increasing, decreasing, or constant part? Yeah, this is your decreasing part. Right? What's this part in the middle here? That's our constant part. And then what's this part over here? Increasing, right? Because we're going from left to right. Now, that's the easy part. The harder part is learning how to label these things. So we'll start with decreasing. Now remember, when we label these parts of the graph for f of x, we're looking for x values. Okay, so what x values are decreasing? Sorry, what x values for the real number line is the graph decreasing? And the answer lies from right here to right here. All right, do you see what I'm saying? That's much better visually than it is for anything else. So we say those x values right there, that would be from -4 up to what point, you guys? -2. Very good, right? So from -4 to -2, because this point right here represents -2, that is the interval for my function is decreasing. What is the interval for where my function is constant? Yeah, in this interval right here. From -2 to 5, my function is constant. From -2 to 5. And notice I'm using parentheses around all of these, because at those points, at the point where they change, like this point right here and this point right there, it's neither increasing nor decreasing, right? It's a point of inflection, so it's changing from one to the other. So we don't include it inside our intervals for strictly decreasing or strictly increasing or strictly constant. So last one, what intervals of x is my function increasing? From 5 to 9. So it's increasing on the intervals from x from 5 to... Okay, so I just put this picture up, and what I'd like you to do is in your table groups figure out what intervals of x is this graph increasing, decreasing, and or constant. So you want increasing intervals, decreasing intervals, and constant intervals. Go ahead and write them down in your table groups for each one. Alright, so let's discuss here. So our first interval would be from -infinity all the way up to the point 1. And is your graph increasing or decreasing on that interval? It's increasing. So we say from -infinity up to the point 1, and we do not include, -1. We do not include the point -1 because that's a point of inflection. Then all of a sudden our graph sort of takes a turn and it dips downward in between -1 and 1. So that interval for decreasing should be from -1 to 1, and again we do not include those intervals. And then our graph turns around and heads back up and starts increasing on the interval from 1 to positive infinity. So we say back up here, we say and from 1 to positive infinity, and we're going to give ourselves any old generic x1 and any old generic x2 in this case. And we're going to give ourselves a function, and the function will kind of look something like this. I don't know. It's definitely some kind of a function here. Call this f of x. And if I want to find the average rate of change between x1 and x2, well then every x1 has an output, and we're going to call that f of x1. And every x2 has an output, and we'll call that f of x2. So if I want the average rate of change between two certain x values, then what I'm going to do is I'm going to plot those points on my function, and I'm going to draw a straight line that connects those 2 points. Anybody know what you call this line if you've taken geometry class? You know what you call that line? It goes through 2 points there? Starts with an S. Ends in an secant. Yep, you got it. This is a secant line, right? Think of circles. If you have a line that goes through your circles, right? And it's a secant line. If it ends on the circle points, then it's called a chord. If it touches through one point of a circle, it's called a tangent line. Okay, so we have a secant line here, and the secant line is connecting the 2 points. Well, kind of. I'll just make that point a little bigger. There we go. It's connecting those 2 points from x1 to x2. Well, the average rate of change for this function is nothing more than the slope of that secant line that connects those 2 points, right? And slope is easy to figure out. So the secant line, or the average rate of change, sometimes I call it the AROC, the AROC, the average rate of change, is nothing more than the slope of the secant line containing those 2 points from x1 to x2. Now, if you want to get fancy with it, which is what we're going to do, we're going to get fancy with it. Remember, the slope formula is just the change in y divided by the change in x, right? So the fancy way of saying this is f of x2 minus f of x1 all over x2 minus x1. So let me explain that. Here is the change in y. It's just the x2 minus x1. That's your numerator. Here is your change in x. x2 minus x1. That's your denominator. So all we're doing is finding the slope of a secant line between these 2 points, and we're calling that the average. Okay, so I've been given a function, f of x equals 2 times the square root of x, and I want the average rate of change between x equals 1 and x equals 9. So what I want you to do is I want to make a visual picture of this. So give yourself a coordinate plane. Okay, and I want to graph the function f of x equals 2x, and we'll use some points to plug in. So we'll go f, and we'll go f of x over here. We'll plug in 0, we'll plug in 1, we'll plug in 4, and we'll plug in 9. All right? So if I plug in 0 to my function, what do I get out of my function? 0. So 0, 0 is a point on the graph. If I plug in 1, what do I get out? 2. So 1, comma 2 is a point on my graph. I plug in a 4, what do I get out? Very good. So 1, 2, 3, 4, 1, 2, 3, 4. Good. And if I plug in 9, what do I get? 6. Very good. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. Sweet. There we go. And I will connect. Like that. And this is the function f of x equals 2 square root of x for these points that we just plotted. Feeling pretty good so far? Good. I want the average rate of change between when x is equal to 1 and x is equal to 9. So x is equal to 1 here, and x is equal to 9 there. So this is 1, this is 9. What's the average rate of change for that function between those 2 points? Well, I can clearly see that that point's on the graph, and that point's on the graph as well. So I'm going to draw a secant line that connects the 2 points. There's my secant line. I'm going to label it.
Wait, I just forgot why those 2 points.
Just because the problem said between this point and this point. That's all. All right, so I have a secant line, and the average rate of change is defined as nothing more than the slope of that secant line. So let's go ahead and do it visually. Let's go up 1, 2, 3, 4. I went up 4 units. I'm going to go over 1, 2, 3, 4, 5, 6, 7, 8. 8 units. So up 4 over 8. Up 4 over 8. That's a slope of 1/2. So the average rate of change for my function, 2 square root of x between 1 and 9 is a slope of 1/2. Now let's also prove that mathematically, saying, okay, let's do f of 9 minus f of 2 all over 9 minus 1. Sorry, this should be a 1. Because we want between 1 and 9. All right, what's the value of f of 9? When 9 goes in, what comes out? 6. So I have 6 minus, when 1 goes in, what comes out? 2, all over 9 minus 1. 6 minus 2 is 4. Oh my gosh, 9 minus 1 is 8. Holy cow, it works every single time. All right, so when we're talking about functions, the last idea of the day here is that some functions are even, some functions are odd, many functions are neither of the two. But let's give you a few examples of each of them and tell you what's so special about them. So for even functions, here's a classic example of an even function. F of x is equal to x squared. That's just a parabola that opens upwards, centered at 0, 0. Another one, even function, is f of x is equal to the absolute value of x. These are some examples. There are many others, but those are the 2 classics. It turns out that even functions, such as these 2, are symmetric with the y-axis. So that means that you could put like a mirror on the y-axis and it would look the same in the mirror on both sides. All right? Now if you compare that to odd functions, here's some classic examples of some odd functions. F of x is equal to x cubed, and f of x is equal to, I have to have x cubed minus 5x. There's some random examples there of odd functions. And it turns out that odd functions are symmetric with the origin. No, we're just calling, what we're calling even functions are symmetric with the y-axis. They're not necessarily have anything to do with numbers. Correct. They're just called even functions, yeah. So let me give you an example of what these pictures look like, okay? So here's one right here. Well, wait, let me give you, where's x squared? Did I have it on here? Yeah, here's one. Let's just do this one. Let's just do y equals x squared. Whoops. There we go. So, parabola, pretty straightforward. Bring it back over here, and check it out. Would you guys agree that it's the same over the y-axis? Right? So if I folded that graph over on the y-axis, it would be the same. Wow, it looks kind of off there, doesn't it? What did I do? Maybe that's just a computer thing. Oh, there it goes. It fixed itself. That was weird. So pretend it's that graph. Okay, so even functions, pretty straightforward. It's the same on both sides for the y-axis. You can fold it in half and it'd be good. However, odd functions, a little bit more funky, right? So let me give you this one down here. X cubed minus 5 minus 5x. I have that one all good to go, and I think it's right here. Yep, there it is right there. Okay, so let's talk about this one. Let's bring this over and talk about it. So in this case, what does it mean for something to be symmetric with the origin? Well, here's what it means, okay? You guys agree that this point right here is on the graph? Okay, could you tell me what you think the coordinates of that point are? 2.2, comma 4. Okay, great. Check it out. Negative 2.2, comma negative 4 is also on the graph. All right, so what you want to do is pick any point, and from that point to the origin, draw a line, and then go 180 degrees in the opposite direction, and that point is also guaranteed to be on the graph. All right, so that's symmetric with the origin. Check it out, it works every single time. This point's on the graph, boom, draw a line in the opposite direction, boom, that point's on the graph. If that point's on the graph, draw a line through, boom, that point's on the graph. They are symmetric with the origin, which is why they're so cool. We just call these odd functions, and we call these even functions. Has nothing really to do with even or odd numbers per se, right? Don't get confused about that part. And there is a test. So how do we test for this? And that's the last thing we're going to do. How do we test for them? So here they're if-then statements. They're going to be this. If f of x is equal to f of negative x, then we can say that f of x is an even function. And if f of negative x is equal to the negative of f of x, then f of x is an odd function. So this is the test of how we perform to see if the function we're given is either even or odd, and I will show you an example of this. No, they're not the same thing. They look the same. This one is comparing f of x with f of negative x. This one is comparing f of negative x with the negative of f of x, and they are different. So let me give you one example because we're really crunched for time here at the end of the day. Let's say we're given this function here. F of x is equal to x times the square root of 1 minus x squared. All right, is this an even function? Is this an odd function? Or is this a neither? Which one is this? So here we go. We're going to check, well, what is f of negative x? Well, that literally means replace every x with a negative x. So 1 minus negative x quantity squared. So that's negative x times the square root of 1 minus x squared. All right, now compare. Are these the same thing? No, they're not the same thing. So it's not even. So let's compare odd. Now, just because a function is not even does not guarantee that it must be odd then. You have to actually check. So what is the negative of f of x? Well, that literally means put a minus sign in front of your function, x square root of 1 minus x squared. Check that out. You get negative x square root of 1 minus x squared. Now, check this out. This function is the same as that function, right? Are those the same? Yeah. They are. So check it out. F of negative x and negative f of x are the same. So because f of negative x is equal to negative f of x, that implies that our function is odd. And odd functions are symmetric with what? the origin. So we're going to graph this and see if it is symmetric with the origin. So we'll go one more, and I believe it was y equals x square root of 1 minus x squared. That says L, huh? 1, there we go. Good, let's plot that on there. Oh, look at this tiny little graph. Look at this thing. Let's zoom in as much as we can. Okay, check that out. Does that look like it's symmetric with the origin to you? Yeah, it sure does, right? If I pick any point, looks like I'll pick this point over here. From the origin, I'll go in the opposite direction. Look, that point's on there as well. Symmetric with the origin. All right.